of the day that I ask you where you've taken class before or a similar class. So, but anyways, let me know if something is going too fast. So I want to go fast, but not as fast so that then not I lose everybody. Okay, so just let me know. Just stop me with questions, whatever you need. Okay, so graphs for us are going to be essentially points and lines joining them. So graphs are going to look like this, where you have a few points. They are called vertices. Um, so, oops, no. Okay, so no. Okay, so graphs are vertices and edges. So in this example of graph, you have the vertices A, B, C, D, and E. And the edges you can call AB, BD, BC, CE, EB. The order in which you list the edges, the two vertices making up the edge, doesn't matter. Meaning that these are, you know, the edges are on order. Pairs of vertices. So even though we list them as sometimes as AB, the edge AB, it really means the set AB. So it doesn't really matter if you list it as AB or BA. So it's very common to use these to represent the edge, but it really means this unordered set AB. Okay. So we're gonna say that it's are adjacent if they are joined by an edge. So that's just vocabulary so that we can talk about that instead of saying every time, look at the edge joining A and B, or if you just want to mean that they are connected by an edge, you just say that adjacent. And then in everything we're going to do, we're going to consider finite graphs. Even though graphs make sense for an infinite number of vertices, infinite number of edges, the ones that we're going to study always have a finite number of both vertices and edges. We're going to see this is important. We're going to see when two graphs are equivalent, when two graphs are isomorphic. In the next section, we're going to talk about isomorphisms. When we say equivalent, we really mean that the same pairs of vertices are connected to each other in both graphs. So here, for example, I have this edge AB right here, and I have it there, as well as my edge BC here is right here. So these are different drawings of the same labeled graph. Uh, in reality, graphs are an abstract object. So you could simply tell me what are the vertices, the names of the vertices and which ones are joined to each other, and I will be able to represent the same graph in many different ways. So these are different drawings of the same graph. But their labels are, the graph here will be my set of vertices. We usually represent this as, that's a graph, that's a set of vertices, and that's a set of edges. For this, the set of edges will be A, B, and C. And the set of edges will be the pairs AB and BC. So this is the abstract way that we define graphs. And so, that's your graph. Then you can draw it in many different ways. And these are just two ways to draw it. The two different ways of drawing them, the same graph, are called equivalent graphs. Because we really think about the drawings, not this, right? Every time we talk about graphs, we don't think about this. We think about drawings. So when I say, okay, these two are representing the same graph. Okay, so that's equivalent. And so this is an interesting easy exercise. They give you the following graphs, and you have to decide which ones are equivalent. And so this is just to clarify things. Here you have You see, these two look the same. However, they are not equivalent because here I have the edge AB, here I have the edge AB, and here I don't have it. So these two are not equivalent. Even though they look the same. Later, we're going to see that these are these two graphs are isomorphic. So they really are like the same thing, but they're not equivalent in the sense that they actually have the same pairs joined to each other. Make sense? And I'm just talking about those two. So for the next one, we can check. We have AB here, we have AB there, we have BC, and we have BC, and we have AC here. So they don't look the same, but they are equivalent. And then we can check the last one. Let's see, I have AB here, and I don't have AB there. So they're not, AB will join those two. It doesn't have to be like that, it could be like this, it could be many different ways, but they're not joined to each other, so they're not equivalent. But again, there is, yeah?
Could you explain more why the middle one is equivalent?
Because you do have the same pairs, right? So both of them, if I don't give you the pictures, both of them have set of vertices, the same set of vertices, right? And they also have the same set of edges, meaning, AB, all the triples, all the pairs, AB, AC, and BC. They are both representing this graph. You can check that A is joined to B, A is joined to C, and B is joined to C, and that's what you have here. So they are representing the same graph with the same labels. They're just drawn in different ways, and you can draw this in many other ways. You could have a triangle just like this, A, B, C. You can also, we haven't talked about intersections, so you could also have like A, B like this, and then you can have, C someplace over here. That's still okay. They're representing the same connections. AB, you just need to make sure that the same pairs are joined to each other. All of those are equivalent graphs.
Got it. Thank you.
Okay, good. So, I already kind of explained this. Here is they're trying to explain to you that the formal definition of a graph, as I was writing it here, is just a set of vertices and a set of edges. And again, we usually, just write the graph as a pair of two sets. The set of vertices, the set of edges. You tell me what the vertices are, and you tell me which ones are connected to each other. That really is a graph. We don't need a drawing. A graph is not a drawing, but it's convenient to represent it by drawings. Mm-hmm. So we already wrote formal representations of graphs. For this one, again, that would be the pair VE, where V is the sets A, B, C, D, E, in any order you want, because that's just the set. And then the edges, A is joined to B, and then B is joined to E, and it's also joined to D, and then C is joined to E, and then also to E. I'm kind of going in order so that I don't miss anything. But the truth is that I can draw these pairs in any order, and here I could have BA instead of AB, all of that. Mm-hmm. So that's the formal representation of this graph. And again, it can have many different drawings. And so all those drawings are equivalent. For example, I can have A to B, and then B to D and E, and then C to D, and C to E. So that's another representation. I'm missing something. Give me 1 second. Because I need to have 6 edges. Let me check. I have a B, I have BE, I
Oh,
have
you wrote
EE.
the CE twice.
CE is in there twice.
Thank you, thank you. CE I wrote twice. It was CE CD. So this was supposed to be CD, I guess. This one. Let me just write it with red so that you know when I change that. CD. Why is I'm missing? ED. Oh, ED. Okay, so I'm missing that one. Yeah. So now they are the same graph. You just need to check that all the pairs are the same. Okay. So so far all of our graphs have the vertices label, but many times, again, most of the times we don't use this representation, we just use a drawing to refer to a graph. And many other times we just draw the graph, but we don't label the vertices. So, you know, still we have a graph, we just don't have the labels, and therefore we cannot, you know, give something like this. But it's clear what graph we're talking about. Now, one important thing, especially if the graph is given by a picture and not by its labels, is that if you have something like this, you know, you have to be very careful to make sure what's a vertex and what's not a vertex. So in this graph, that's not a vertex, right? And in the other one, it is a vertex. So they look the same, but we need to make sure to identify what's a vertex and what's not. If we were to give labels to these graphs, you know, we could say those are the vertices A, B, C, D, and you only have the pairs A, C, and B, D. Again, by convenience, we list the edges like this, but they really are pairs, you know, sets of 2 vertices. And here I could say this is A, B, C, D, and E. And so the edges are AE, EC, DE, and EB.
Sorry, I had 2 quick questions.
Yes?
The red line between from points E to D, why is that red? And why is D yeah.
Just because at the beginning I made a mistake here. So I just made it red so that if you had it in your notes as I had it at the beginning, you know, it kind of pops up when you see it in my notes and say, well, I used to have an E. So this was a typo I had before. I just kept the different colors so that in case you still had the typo in your notes, you can.
Okay, is that the same thing with that one?
Same thing. I was missing this edge and I realized something was wrong because here I had 5 edges and here I only have, I have 6. And so I checked everything and that's when I corrected that and I added that. The only reason why that red is that it pops up if it's different to your notes.
Okay.
All right. Okay. So we usually talk for most of the semester, we're going to talk about what's called a simple graph. And I'll explain what it is, but sometimes we do other things. We consider other types of graphs. So, you know, these type of things can happen in a graph. You have a vertex joined to itself, or you have 2 vertices joined to by 2 different edges. So these are called multi-edges and these are called loops. And the way that I was writing my graphs before, I said that that was a set, and I said that this was also a set. So in a set, I'm not allowed to have, for example, CD twice. If I do, they're actually representing just one element, right? So if I want to use this type of notation for my graph, and I say that B and E are sets, then this doesn't happen. This doesn't happen because that would be it wouldn't really be a pair of different vertices, so that wouldn't happen, and I wouldn't have multi edges because I would be listing the same element here. But still, it is incredibly powerful to consider these type graphs that contain these things in terms of the applications. You know, if you wanted to use graph theory to solve a real life problem, many times you have double connections. Like, I don't know, if you're thinking about the Facebook graph that connects friends, maybe you have two friends, two people that are represented by different accounts or something, but so that they might be friends twice, in two different ways. I don't know. Um, yeah. For more important applications, you might have chips in a computer that are connected in two different ways. Or you can have a chip that's connected to itself for some reason. So, it makes sense to consider graphs like this. But in that case, we have to specify that the set of vertices is a multi-set, or the set of edges is a multi-set, and the edges can actually be pairs of the same vertex, A to A, or if I were to label this as A, and this as A, let me say B and C, then here I will have the edge A, which is not a set, right? And here I will have BC twice. So anyways, sometimes we consider multigraphs, but for most of the time we consider simple graphs, which are the ones that do not include these things. So let me just say here, simple graphs do not allow loops or multi-edges. The ones that do allow that are called multigraphs. But most of the times we use simple graphs. Most of what we're going to see is for simple graphs. Any questions so far? Okay, so let me go to the next page. Okay, so one more kind of graph. So these are like the modifications to my original definition of a graph. So I defined you what's called a simple graph. Then I told you that we could have multi-graphs, meaning loops, including loops and multi-edges. And then we can also sometimes, especially for the applications, we can direct the edges. So for a directed graph, which is usually called a digraph, so a directed graph, a digraph, those are the same thing. The edges are, the edges are directed. So in a graph, the edges look like this. In a digraph, the edges are arrows. Mm-hmm. And for example, if you want to use a graph for a system of streets, some streets are one way, so you want to have just the arrow in the correct direction. Some streets are two-way streets, so maybe you want to have something like this, and that's not considered a multi-edge. Mm-hmm. Those are like different edges, and so whereas in this one you will have the edge AB as a set. In this one, you actually have the edge AB, which is order, and so which is different from the A, which will be the edge that goes in the other direction, right? So if you're talking about digraphs, then you need to make sure that you list the vertices forming the edge, the directed edge, in order. But again, most of the times we're gonna just use simple graphs, no directions, not anything. In some of the applications, you're actually allowed to mix some of the edges being directed and some aren't. But we're gonna see a little bit about the graphs at some point. But we're never gonna use mixed graphs, at least not for this class. But it is used in many of the applications. Okay, so from here, these are like special families of graphs that we're gonna use for many different things. And so we just kind of name them in a specific way instead of trying to show a drawing, or maybe maybe we want to refer to some of these graphs with 100 vertices. So we want to have a notation for that instead of having a drawing explaining what it is. So the first class is the class of complete graphs. That just means that all the pairs are joined to each other. So you tell me how many vertices, and then I know that all of them are joined to each other. So this is K1, K2, K3, and the K comes from complete, the word complete in German. So it really comes from the German. So K1, K2, K3, K4. These are two representations of K4. No? But they are both K4. K5, two representations again of K5, and there are many others, of course. And so, for example, if I give you K6, if I wanted to draw K6, then you just need to have 6 vertices and join all the pairs. So one possibility is to do it like this. I have the diagonals, and then I have these triangles in the middle. Just join all of the vertices. A cleaner way to represent K6 is maybe having this triangle right here, and then having another small triangle here inside. Now I have my 6 vertices already, and I have to join all of them, all the pairs. And you can check that I actually did all of them. Mm-hmm. So this is a little bit easier to understand, I guess, a little bit cleaner because you have less crossings. We're going to talk about crossings, how to ways to draw the same graph with less crossings later on in I don't know, I think it's section H maybe, I don't know, but it's one of the sections that we're going to talk about related to crossings.
Professor?
Yeah.
So, can we consider the shape, the graph that's linear, that all the vertices in their same line?
Yes. So that would be, there are many other representations. For many of the applications, sometimes you want to have them 1, 2, 3, 4, 5, 6 on a line like this, and maybe, there I have the consecutive ones, and then I have the ones that will skip 1, maybe like this, and okay, and then the ones that skip 3. And maybe to make it a little bit clearer, I can so that one is going to be the first one, the second one, the third one, and using the fourth one, and the last one, and then that one is missing. So look, I'm looking at what is joined to the first one, to the second one, to the next one, to this one. It's missing the last one, and then each one needs to have 5 around, right? So 1, 2, 3, 4, 5, because each vertex is going to another 5. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This one has already 5. This one, 1, 2, 3, 4, 5. Yeah, it's done. So everything is going to 5. So something like this is also a possibility.
Professor. So does complete mean that every vertices touches every edge, and that's it?
Yeah, that's all it means. Complete means all pairs of vertices, each, or maybe all pairs of vertices are edges. That's all it means. And so, of course, you can do it in many different ways. You just pick any 6 points and join all the pairs in any way you want. But all those graphs are essentially, all those drawings are representing the same graph. So again, we're going to talk about graph isomorphisms because what I'm really saying is that these graphs are essentially the same, but I don't have the label for anything. So are they really the same? So we'll talk about isomorphisms in the next section, just to make, that will essentially make all of this the same thing. Just drawings of the same graph. The next family are cycles. cycles just look like, you can think of the cycle as a regular polygon, and then all the ways that you can modify the drawing of that polygon, all the ways of representing that same graph. So here I have C3, but again, it doesn't have to be done that way. I mean, I could do crazy things for the cycle. I could say, okay, I'm gonna join these two like that, and then I'm gonna join these two like this, and then I'm gonna join these two like that. That's another C3. It's just, it doesn't give us much information as looking at this one, but that's still a drawing of C3. I just have all the, I have a cycle. I have a cycle that visits all the vertices exactly once in some order, right? So I can think of this as the regular polygon, and then all the different ways that you can draw that polygon. So here, for example, two drawings of C4. You just need to make sure that you start one vertex and you have a way to visit everything and come back. It's just like that cycle. C5, two different representations of C5, C6, C8, and you can do any crazy thing you want. It just needs to be like a circuit that goes through all the vertices and back. And those are all my edges. Okay. And of course, there are many more. These are just two representations of C5, but I can make many more. I can make one that's on a line 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Or I can make it. Like 1, 2, 3, 4, 5. Something like that. That will also be a C5. There are many different ways of drawing C5. Okay. So those are cycles, and you can see cycles included in other graphs. Like, for example, here, if I highlight these edges, so that's a C4 that's containing a K4. So we're going to start talking about subgraphs. And cycles and complete graphs are the special subgraphs we're going to have. Anyways, so a cycle, as I was saying, you just visit some vertices. It's like instructions to visit vertices in a certain order, and you go back to the original place, to the starting place. And so paths are just, you start someplace and you go through your graph, just following some edges. So for example, here, so let me see. This is one way to represent a path in this graph. So I start at A, I use AB. Then I stop at B and I use BC. And then I stop at C and then I use CE. And I finish at E. Now, this representation for this path is a little bit redundant because, in order to actually be a path, which is just a series, imagine that the graph is representing streets and the vertices are representing corners. So, if I'm actually going from A to B, the next vertex has to be B. That's the corner for the tunnel. You do something else. So this notation for the path is redundant. You could simply write it as go from A to B and then go to C and then go to E. And you are assuming that, this could be my path, A, B, C, E. And we are assuming, this assumes, there is an edge from A to B. There is an edge from B to C. There is an edge from C to E. But you don't need to list everything like here. It's a little bit redundant. So paths are usually represented like this. And if it is indeed a path, then there needs to be an edge between A and B, between B and C, and between C and E. Okay.
So the path you just wrote, that's acceptable or it's not?
That's a what, sorry?
It's okay to write the path the way you just wrote it?
Yes, and that's usually what happens. That's the way that we usually write them. So let me see if there are some examples right here. Oh, here they have another path. Let me let's see. I should have made a copy of this. Oh, okay, so I'll just do another one. Sorry, sorry, sorry. Okay, so let's say that I have A, B, C, D, E. Yeah. So suppose that I have that graph and I decide, you can look at paths just like this. Here to here to here. Let's say that I'm actually gonna go using red first and then the yellow one. Okay? So so I use down first, then this one, then this one, then that one, and then that one. So my path, so I can actually repeat vertices. I'm gonna repeat E, as you're gonna see. So I start at E, D, C, A, E, B. That's my path. And that assumes we write them like that. But that assumes that as in here, all of these vertices, I'm able to visit them in that order. So that assumes that ED is an H, DC is an H, CA is an H, AE is an H, and ED is an H. If they weren't, then that wouldn't be a path. So for example, if I just list something arbitrary, E, C, B, A, let's say, that's not a path. Because EC is not an H. All right. Okay. So let's see. So this is kind of all of this. All of this is the explanation of don't use this redundant long representation of the path. Better just use something like this. The important thing here is the length. The length of the path is defined as the number of edges in the path. So in my previous paths, let me just go back very quickly to the two examples I had before. So this path has length 3 because it uses 3 edges, and this one has length 1 to 3 red ones and 2 yellow ones, so 5. Length 5. One less than the number of vertices, or than this list, the number of vertices that you see here. So 1, 2, 3, 4, 5 edges. Okay. All right. So those are paths, just regular paths. Here, let's go over A3 just to double check. Find a shortest path. So from path of minimum length from A to B. Is your path a simple path? Oh, I should have lighted this too. So simple path is that you don't repeat vertices. So let's see. So this exercise just say find a shortest path from A to B. So let me start with something that's not the shortest, just to make a point. So let's say this is let me copy paste this one. So this this is a path and it has length 6. Remember, your start at A is from A to B. And so I go 1, 2, 3, 4, 5, and 6 edges. Do you see something shorter than that? Well, we don't have labels, so it's hard for you to tell me what, you know. But let me show you one. So what if I go like this? 1, 2, 3, and 4. And actually, oops, let me copy paste this one again, just so that in case we see something better. So here, 1, 2, 3, and 4. So that one has length 4. And we're looking for the shortest one.
Why is the length 4?
For it's 4 edges.
Oh, I see.
4 edges. So that's supposed to be a 4 edges. How many edges you use? That's the length. And I don't see anything smaller. I see others that are 4. You know. Let me make another copy just in case. Because once I draw on top of it, it's harder. So, for example, I see this one. 1, 2, 3, 4. That's also length 4. But I don't see anything that's less than 4 edges. No? And so here's the thing: I need to use that edge for sure, right? Because that's the only one that gets to be. So that was 4, so I need to use it. And so the only way that I can get to A in less than 4 edges total is if I could go in 1 or 2 edges to A from there, right? So from here, I need to get to A in 1 or 2. I cannot get in 1 because they're not joined to each other. So the only way that I could do this is if I can get in 2 steps, right? In two edges. So, but you see, if I use that one, I still cannot get to A directly from here. If I use that one, I cannot get to A in the next one. And if I use that one, I cannot get to A. So I won't be able to make 3 edges. So we're going to have to give this argument that, you know, the fact that you can find one with 4 and you cannot find one with 3 doesn't prove that that's the shortest. We're going to, in the next few lectures, we're going to start proving things. So I gave you an argument, but that would be a proof. But we're going to get started with how to put things in graph theory. They're very worthy. You know, it's not like in calculus that maybe you can get away with writing by theorem base or not even just some computations will prove things. Here you have to actually write some sentences to prove that that would be the shortest. Okay. Anyways, we'll get to that later. But the shortest has length 4. In the same graph, find a simple path from A to B that is not the shortest path. It could be the blue one. Mm-hmm. Explain the relationship between simple paths and shortest paths. Joining. Oh, I didn't answer the other part. So it says find the shortest path from A to B. Is this a simple path? A simple path is one that doesn't repeat vertices. So let's see. Let's just look at all the ones that I use. That's simple. I'm not repeating vertices. This one's simple. And this one I think is also simple. You know, this, that. That one is also simple. So all of mine are simple. But just to give you one that's not simple, let's see if I can. Yeah. So let me give you one that's not simple. So I could go like, maybe I can go like this. here. Mm, mhm. Yeah, I don't know. I could go like this and then back and then here, here, and here. You know, that would be a path that's not simple. Let me call them A, B, C, D, E, F, G, H, K. So this path would be B to C to B to C to E to F, B to C to B to C, oh, B, C, D, C, F, E, A. And so here I'm repeating this vertex, so it's not simple.
Does it
But all
matter
the other-
starting with A instead of starting with B?
Oh, okay, thank you. Yes, it doesn't really matter, and I traversed it backwards. But yes, you're right. They said from A to B, so maybe I'll just do A, E. I'll list them backwards: F, C, B, C, B. But they're really the same path, no, same path.
Would it
But
matter? I mean, would it be wrong if you did specify like A to B and rewrote it as B to A? Would we be marked wrong or anything?
well, in general, you'll see. So in this case, they actually specified from A to B, so I should be using that. But the paths, they're the same. So if they ask you to write a path from A to B, write that one, right? The one on top.
Okay.
The other one is from B to B, from B to A. But you'll see that in general, it doesn't really matter. It doesn't matter. So we're not going to ask for a path that goes from here to there. We're just going to ask for paths that join two vertices. Mhm. Or they can ask you, what is this path? Let me say it this way. In this particular question, they say, find a path from A to B. And as you can see, I just drew them. So, you know, I didn't actually specify the vertices. But if you're asked to specify the vertices, please go with, you know, start at A, finish at B. But, you know, most of the time, you just want a path that joins A and B. So it doesn't really matter how you list it. Or if they give you this graph and they ask you what is this path, it doesn't matter how you list it. It's just because in this particular example, they did say from A to B.
Excuse me,
if they say
question.
from A to B, yeah.
Sorry, I'm wondering too about what Samuel Royas was pointing out because I was thinking the exact same thing. In the chat, why can't it be A, E, F, C, B? Oh, non-simple.
Well, it's not simple because you have to see.
So if it's not simple, are we supposed to also include G, H, J, and D, not just D then?
No. So in your graph, you can have many other vertices. The ones that you're using for your path are the ones that you list, and you list them in order in which you visit them. Okay, so if we're talking about this path that I highlighted, you're not going to use G, H, and D for anything. In my path, I specify, you know, I highlighted, my path is actually what I highlighted here. And so it's not simple because I'm repeating that vertex. All the others are simple, and I didn't list anything. You can just check that you're not going over the same vertex twice. So I didn't even list them. But if I were to list them using those, you know, those labels that I made up, then you will see that I'm not repeating any vertex at all. So for example, if I use the same labels here, maybe, let's see, G, H, J, C. And my question is there something on the chat? I don't see anything on the chat. Where's my chat? Um, oh, okay. I didn't see anything else. But now I see the chat. Okay. Why can it be A, E, F, C, D? A, E, F, C, D. Yeah. So, okay. Okay. So let's see. Well, guys, I didn't see the chat at all before. I didn't get any notification that there was something in the chat. So I'm just looking at it right now. So let me write the same labels for this one. C, J, K, H, F, E, and D. Okay. So this one, the red one, is A, E, F, C, D. Whereas this one right here, is A, E, F, E, C, C, B, C, D. Mhm. So that
It's a-
different paths. This one
it's
is
a B.
simple.
To be at the end.
Oh, thank you. Again, mhm. That different paths.
Wasn't the second one not simple?
The second one, meaning this one.
No, the one with the black writing, with the blue and the red highlighting.
Oh, this one. Oh,
Yeah.
oh my goodness. Yeah, that's not simple because I'm repeating the C down. The other one is simple. Mhm. And all the others are simple. You know, the blue one right here is A, H, J, E, F, C, D. That one is simple as well. I'm not repeating any words. But let me maybe this
Oh.
will clarify things.
So
Yeah.
the use of simple doesn't mean the shortest path to B. It's the
No,
okay.
exactly. So okay. So let me write it here. So simple means that vertices are not repeated. Shortest means the smallest possible length. So they're two different things. But they're trying to make a point that if you actually repeat the vertex, it's definitely not the shortest, right? Because you can cut right there. You know, first time you get to Venice, you go around and do other things. You get back to Venice again, and then you can continue. If you cut that loop that you did, then it's going to be a shorter route, right? So the point that they're trying to make is that if a path is not simple, if a path from A to B is not simple, then it's definitely not the shortest.
Professor, I had a quick question regarding the definition of simple.
Mm-hmm.
So, by saying that vertices are not repeated, does that automatically imply that we're also not repeating edges?
Yes.
Okay.
Yeah, so that's a good observation. Mhm. Yeah, but there are cases, and let me go back because I think that the path that we had here, this one. So this one is simple, and this one is not simple. And this one is not repeating edges, but it is repeating the vertices. Uh-huh. And you know, it's not the shortest joining, let's see, this is E to B, right? So it's not the shortest joining E to B because you could, you're starting at E You do something and you go back to E and then continue. So you can just cut that loop that goes from E to E, and you will have a smaller, shorter path. Uh-huh. So if you were looking at paths that join E to B, the shortest is just the edge EB. Mhm. Okay. Mhm. So okay, and so one more thing here, find the longest. So shortest, longest is just the definition of the word in English, right? The least number, because the way that we define length is by the number of edges. So longest, shortest means the smallest number of edges, and longest will mean largest number of edges. So here they're asking you find the longest simple. So that's important. Path from A to B in that graph. Uh-huh. So you want to use as many edges as possible without repeating vertices to go from A to B. Mm-hmm. That question makes sense, and probably the one that I did. Let's see, is that probably that one is longest. Um, like I cannot include D if I don't want to repeat vertices, because once I go to D, I have to go back to C. I would use that edge twice, so I cannot use D. The only question is if I can add G to my path without repeating vertices. I don't think so. So I think that one's going to be the longest one. And then this other question, why is it not possible to talk about the longest path joining two different vertices in the graph? And I don't know if that makes sense to you. So here I'm asking for the longest simple. Here, if I were asking only for the longest path, then it wouldn't make sense, because I can just, repeat the edge going back and forth, back and forth, back and forth. And so my path is never going to be the longest. I always can make it longer and longer and longer. So it doesn't make sense to ask for the longest path. Mm-hmm. Unless I require that to be simple. So the answer here is we could use an edge as many times as we want. For example, in that picture, we could have AH as many times. Oops, sorry, yeah, AH as many times as you want, and then continue. AH, let's say G. So that would be like the yellow one. G, C, B. So that would be like the rest of the yellow one. But then here in the middle, we can add as many copies of H as we want. So we cannot talk about the longest, because we can make it longer and longer and longer. There is not one that's the longest. But if I ask it to be simple, then the question makes sense. Okay, and remember, this is the first discussion about paths. We're gonna be more precise, and we're gonna have more later. This is just a definition. It's just some examples. We will click more later. Okay, so here we have open paths and closed paths. Open, open, and close. And that's just imagine the open ones as starting someplace, and then you go visit other vertices and finish at a different place, or just over here, you move along the graph and eventually return right here. Mm-hmm. So of course, in my picture, there's supposed to be vertices, all around. Okay, so here's the thing. We said that simple means that we don't repeat vertices. So a closed path cannot be simple because I am repeating the beginning and the end vertex. But we still want to have a word for a closed path that it's only repeating the starting and the end vertex. So that's going to be a simple cycle. So here, so we have cycle graphs that's we defined earlier. So the cycle graphs are this one's right here, CN. Oops. So those are the CN that we defined in the previous page. But we also have cycles in a graph. And so a cycle in a graph is just a closed path where the only repetition is the beginning and the end. So it's almost simple. The only repetition is the starting and ending vertices. So maybe I'll say just almost simple. So the only repetition is the beginning and the end. So it says here, find 3 cycles of length 3 in this graph, so such that each cycle includes a different set of vertices. So we could have, let me make 2 copies of this graph so that I can actually draw them. So we can have, it says cycles of length 3, so that look like triangles. So I can have this one, set of vertices as A, A, B, E. Here I have another one, and here I have another one. So those are 3 different copies of C3 inside my graph. So you can think of a cycle in a graph as a copy of Cn. So this way, like, or think of copies of Cn in a graph. Okay, so this is like a C3 inside your graph, a cycle of length. Questions? Okay. Okay. Okay, so let's go over subgraphs. Actually, you know what? Let me go over this last part as well. Um, let me do this. How do I do this? Okay. Give me 1 second. Okay. So, okay. So I just wanted to finish with this problem right here. So this one right here. So it says in the same graph, find 3 cycles of length 4 such that each includes a different set of vertices. So here, I need one more copy. So cycles of length 4 I can have this. I can have that. Those are two cycles with different vertices. Maybe I should give you one more so that you don't get the wrong idea that they always need to look almost like a quadrilateral, convex quadrilateral. So here's another one. They can look like this. Oops. So that's another copy of C4. And it says, explain how you know that there is no cycle of length 5 in this graph. So look, if I wanted to, again, we're not going to be very rigorous right now, not yet. But if I wanted to find a cycle of length 5, then that means that I need to use all of the vertices, right? I need to use all of the vertices for a cycle of length 5 because I have 5 vertices total. So that means that I need to use these two edges, right? I need to use those two edges because I need to use C, and those are the only two edges that go to C. But I also need to use these two edges, right? Because those are the only two edges that you see. And actually, you know what? I will make another copy of this one. So I need to use those, and I need to use this. With both in the same copy of C5 if you wanted a C5. But then when I put them together, that already closes a cycle. So this one and this one closes a cycle. And so I cannot add A. I will need to use, I cannot add A because then I would have I will have 3 edges coming together right here, or 3 edges coming together right there. I won't be able to do a cycle. I already completed a shorter cycle, and so that cannot be included in a C5, in a pentagon, let's say. So let me just say here to finish, we cannot extend these to a cycle with 5 edges. Okay. So, subgraphs. So those are just almost like subsets of our graph, subdrawings, if you want, of a graph. So here I have this graph, and so I can take any vertex by itself is a subgraph. So I can take the vertex A or B by itself, or C by itself, or any set of vertices with no edges. That would be a subgraph. I could also take just an edge. I could take some of the edges. So you just some of it. I can take some of that graph, and that would be my subgraph. So I can have more. I can have, for example, I could also have like all the vertices A, C, and just remove a few of the edges. So that's also a subgraph because I'm missing this edge. So just remove a few things. The only thing you need to be careful about is that if I remove a vertex, everything that's attached to that vertex is also removed, because the only thing that I cannot do is say remove B, but I leave that. That doesn't make sense, because then if there is no vertex, then there's no edges. Make sense? So I can remove anything, but if I remove a vertex, I remove everything that's attached to that vertex. Okay? That's a subgraph.
Professor, I have a question.
Yeah?
It says BD is not a subgraph, so why is that? Aren't we removing the C?
BD. Oh, okay. No, because remember, these are pairs, right? So when you have this drawing, what it means is B is a friend with C. Think of this as friendship, or think of this as streets. Here this means B is friends with C, C is friends with B. Does that necessarily mean that B and D are friends? No. Or think about this. There is a street between B and C, and there is a street between C and D. Does that mean that there is a single street that joins B to D? No. Mhm. So these are pairs. These are pairs. The pairs are AB, BC, CB, and AD. Those are my 1, 2, 3, 4. I'm missing one. A, B. Oh, I'm missing AC. Those are my edges, right? In my original graph. And these are my vertices, A, B, C, and E. So any subgraph will have a subset of the vertices and a subset of the edges, but it needs to be itself a graph. So BD was not an edge originally, so it cannot be an edge of a subgraph. The fact that they looked aligned, it doesn't mean that there is something joining them. Remember that that graph is equivalent to this graph. And I think in this one, it's clearer that BD is not there. These two graphs are equivalent. And BD is not there. So the fact that they're aligned doesn't mean that D is joined to B. You can go from B to D with a path, but not with an edge. Okay? Here's my chat. Okay. How can we tell if the graph is a cycle or not? We're going to see more. We're going to talk about degrees of vertices in 1 second, and you'll see that the cycles have, all its vertices have degree 2, and they are connected. So we'll get there. How, to the question, how can you tell if the graph is a cycle or not? We'll get there. Okay.
Yeah, I didn't understand. Sorry, I have a question. I didn't quite understand the cycle with the need both in the same copy of the 5th cycle. I'm not sure if you can go over that graph again.
Oh, for this exercise, for this example?
Yeah.
So this was in regards to this question C. This question C. So it says, explain how do you know that there is no cycle of length 5, right? So what I was saying here is that if there were a cycle of length 5, then you need to use all of the vertices, right? So a cycle of length 5 will use all vertices because there are only 5 vertices, right? So I need to use them all. If I need to use C, then I need to use all those 2 edges, because in the cycle, I start at some point and then I visit all the points, all the vertices, and then I go back to my starting point. So at some point I need to visit C, and the only way to visit C is if I use that edge and this edge in one direction or the other, but I need to go through it, so I need to use them. So we need to have that. But we also need to visit D, so we need to use this. And if you prefer, instead of the way that I was doing this here, another possible explanation is that I also need to use these 2 edges. I also need to use these 2 edges because I need to go through A. I need to go through A, so I also need to use those 2 edges, which means that I need to use 6 edges, but I can only use 5. A cycle of length 5 has 5 edges. So that's another possibility. What I was trying to say here is, if I need the red edges and I need the blue edges at the same time, then this needs to be part of my cycle of length 5, but it's not possible. A cycle of length 5 only repeats the starting point and the end point. And so C4 is not included as part of C5. But if you want, you can disregard this and you can say, all these 6 edges must be in my cycle, but the cycle has 5 edges. Mhm. So let me just write that here. All those 6 edges must be in the cycle of length. Well, right, so you have 6 edges that must go in a cycle that only has 5 edges. Mhm. So that's another perspective. But again, we don't have a lot of, we're just starting with the definition, so we still don't have a lot of the tools to formally explain this. This is supposed to be just to get you started thinking about graphs, things that can happen and things that cannot. Okay, but we don't have enough of the tools, right? First, very important tool is going to be the degrees of the vertex you're going to see. So this is really where we're going to start seeing some tools and results that we will be able to use. So you'll see that later on we'll be able to say this in other ways that are probably easier to understand. So, okay. So here we go. We have subgraphs of a graph, and then we have the complement of that subgraph. The complement is just everything that you remove. So let's say in the previous example, well, first let's look at this one. So actually, let's do this. No. So let's just talk about complements in general. So it's you have these vertices A, B, C, D, E. You have the same set of vertices. Whatever edge is not here, whatever curve that's not joined here, it's joined there. That's the complement. So it's like the complement to the complete graph. So here we go. So A is joined to B, but it's not joined to B, to E, or to C. So you join them to B, E, and C here. The only vertex B is not joined to is to C. So you do it here. Huh? So this is G. You can say that this is G, and this is G complement. And I think that we complement G. We represent it with the line. Okay. So this is the first definition that would allow us to prove some things. So that's the degree of a vertex is just the number of edges that are incident to that vertex, or in other words, the number of edges that are attached to that vertex, or the number of edges of which the vertex is part of. Remember that the edges are paired vertices. So in the drawing, it's very easy to see. So I can list the degrees in this graph in red. That would be degree 2. There's 2 lines attached to it. This would be degree 3, degree 3, degree 3, and degree 1. And then for this one, that's degree 3, degree 2, degree 1, 1, and 1. And let me just note here, since we have the graph and its complement, note that the sum, actually I'm going to denote this with the use D of A in the book. Many times I think it's a little bit more standard to use DEG for degree of A. And if you're talking about different graphs at the same time, you can use the name of the graph as a subindex. So you could also write D sub G of A, because sometimes you're talking about different graphs at the same time, so the degree in one graph can be different of the degree in the other. As an example here, if I take the degree in the graph G of A, I can also take the degree in the graph G complement of A, and that gives me 4. You see that 1 plus 3 is 4. Yeah? So let me just say here, it's the only thing I'm saying is 1 plus 3 is 4. Okay, but
So
you can
why
also
do you
take the
have, or oh, sorry to interrupt you.
go ahead.
Graph G, why do you have where the vertex B and D? Why do you have 3 and 3 for B, D, and E?
It's just how many lines you have attached to that vertex. So the degree, that's what the degree is.
Oh,
So
okay.
for
Yeah.
this one, 1, 2, and 3. That's what the degree is. And then for this one, 1, 2, and 3. And for that one, 1, 2, and 3. That's why they all have 3s. And then for this one, I have 2. And for this one, I have 1. Okay, so just count.
I see. Oh, okay. Thank you.
So those are the degrees. 2, 1, 1, 1, 1, 2, 3. Those are the degrees. Mhm. And so my note here is, you see, what happens if how the degrees of the graph of a graph in its complement relate to each other. Oh wait, I'm over time. Sorry guys. So that's what I was trying to to write here. But we'll continue from here on Thursday. Okay, so I'll start right here with the degrees, and then I know it could be a little bit overwhelming because it's a lot of definitions, but you'll see that this is just the vocabulary to be able to talk about graphs. We'll start seeing actual results next class. Once we go over this definition, we'll have our very first actual result next time. Okay?
Thank you,
All right,
Professor.
guys.
Okay, thank
I'll
you.
see you next time. Thank you. Sorry for running over. I didn't realize it was already 12:17. So I owe you 2 minutes. Bye, guys.